morning, everyone. Good morning, Cassandra. Good morning, Justin. Good morning, Rachel. How are you doing today? All right. So, Rachel, I have your question. I haven't been able to sit down and answer your question, but I have it here. If you want to stay after we finish the class, so we can go over your question. Okay. If not, I can send you my response via email. All right. So I want to start our class with a quick review of a few key concepts from Unit 5 and Unit 6. First thing that you are seeing here, this is taken from the worksheet of the day related to Unit number 5, is, here I'm missing a factor here, oops, right. So here we have x minus 3. All right, so here, what we want to do, we know that all these concepts, x-intercepts, a 0, a factor, a solution, a value of 0, all these are equivalent concepts. But we want to make sense with the context that we are talking about. If we are talking about the graph, you want to refer to 3 as an x-intercept of the graph f, right? When we're talking about, when we're talking in the as a polynomial function context, so 3, we refer to 3 as a real 0. When we are evaluating the function, the polynomial function, with x equal to 3, then its value is equal to 0. This one is important. I saw a lot of people doing the following, like something like this. This is something that I believe if you write something like this, you want to write like a coordinate. But when we're talking about a factor of the polynomial function, we use x minus r. This is the structure, and r, the value of r in this case is 3, because 3 is a root of this polynomial function. And when we are in the context of an equation, like this one, we said that 3 is a real solution, right? So I took points away from this one. If you use 0 here, it doesn't mean, it is not wrong, but it doesn't make sense in the context, okay? So we want to make sense in the context that we're talking about, all right? So that's important. From this one, a lot of you did a very good job here. The only thing that I'm going to be very picky is that if you are going to omit a, the value of a, okay, because you are going to choose, because you are choosing the value of a to be equal to 0, to be equal to 1, then you need to write in a corner of the page that you are using a1 as the value of a, okay, so the leading coefficient, right? Because when you do this, you are telling me that you understand all the part that make up a polynomial function, the leading coefficient and the factors, okay? So if you are in the test or in the quiz, you want to use one part of or you want to write a equal to something, or a equal to 1 as least, and that is going to tell me, that's the way you are going to tell me that you are taking into consideration the value of the leading coefficient, okay? Okay. Another thing that I wanted to discuss is when we use this table to determine the behavior of the graph at the x-intercepts, I want you to tell me here odd, or even. 1 and 2, a lot of you use the value of the exponent, 1 and 2. Instead of giving you 2 points, I took 1 point away because yes, that's the exponent, and that's completely correct. But since the purpose of this table is to determine the behavior of the graph at the x-intercepts, what you want to be when you want to put here in multiplicity is odd or even, because odd or even are the two categories, right? Yes, 1 and 2 are also correct, okay, but I want to see you writing the categories. The multiplicity is odd, the multiplicity is even, hence the behavior of the graph at the x-intercepts. Okay. So that's the quick review for unit number 5. For unit number 6, so here, when you are listing all the possible rational zeros, do not forget the plus minus. Remember that we are going to take into consideration the positive and the negative value of each entry on this list. And also, I want you to show me how you are getting the numbers, okay, the element of the list. So positive and negative 1, 3, and 9. So you need to show me how you got those numbers. All right. So something like this is going to be enough, where you show all the factors for the constant term, the constant value, and the leading, all the factors for the leading coefficient, and then the combination, right? Careful here, when we know that based on the degree of the polynomial is the amount of zero that we are going to have, but this is the total number of zero, and when we use that phrase, we are referring to both real and complex zeros. When the word real, or the adjective, I believe the adjective real is being used for the zeros, you need to take into consideration the type of zero that we have. So here, the question is about the real zeros. As you can see here, this is a representation of the graph. We have only one x-intercept, meaning we have only one real zero. From that zero, we can get the roots of the polynomial, r equal to -3. We know that the value of the function, of the polynomial function, when x is equal to -3, is 0. Hence, the factor, remember that we use x minus r, so x minus -3 is x plus 3. Okay, and then when we are going to do the synthetic division, we need to take into consideration the sign of that 0. -3 is a root of that polynomial. Then we need to use -3 in the synthetic division. Okay, lastly, let's talk about how we do the downgrade of the degree of the polynomial to get the depressed equation based on the division of the renal equation by one of the factors. The equation that we are working in this exercise, yes, okay, has a factor form of, and I'm going to write the factor form just using the real zeros. So it's x plus 1, x minus 2, and then it is 7x squared minus x plus 1. Okay, from this last factor, this quadratic factor, is where we get the two complex zeros, okay? But before getting to the complex zeros, so I want to explain how we go from a degree of 4 to a degree of 2. From the graph of this polynomial, which is here, we can see that we have two real zeros, x equals -1 and x equals +2. Because these are two roots of this polynomial function, we can go and determine that we have a factor of x plus 1 and a factor of x minus 2, right? So that's the relation that we have between the roots of a polynomial and its factors, and its linear factors. All right. So in this exercise, we are looking for all the zeros of this polynomial. Okay, so I should put this here. Okay, so here we have the standard form. Okay, the standard form and the factor form. I should put this number here. All right. So what we do in order to find all the zeros of this polynomial? Well, we identify one rational zero, or one real zero. In our class, we are identifying one rational zero. Then we use that rational zero to get a linear factor, and using that linear factor, we do the division to get the difference equation. What is happening when we do the division? So in this first step, where we take r equal to -1, so x plus 1 as a factor, and then we do the synthetic division of the polynomial by -1 to get the difference equation. What is happening here? What is the meaning of doing this? So you have here the factor form, right? All right. So what is happening here? So when we do this process, what we are doing is that we are dividing the entire polynomial by the factor x plus 1. And when we do this, okay, when we do this division, we cancel that factor. Hence, we got x minus 2, then x squared minus 7x squared minus x plus 1 as the quotient, right? The remainder is 0. So see what happened in the difference equation. Now we don't have x plus 1 as a factor, meaning that the r, or the 0 of equal to -1, the 0 of the polynomial -1, is not in the difference equation. Okay. So at this point, if you have taken out one linear factor, x plus 1. So if you want to continue from this quotient to find other zeros, you cannot use -1 because you already used -1 to take out the factor, the leading factor x plus 1. So that means that in the next step, once you use -1, which is 1, 0, you use -1 to divide the polynomial and to get the depressed equation, which is, this is the depressed equation now. This depressed equation does not contain -1 as a 0. So then you want to use the other 0, which is r equal 2. That means that now you are going to divide by the factor x minus 2. Okay, so now you are going to do this, you are going to take this, and you are going to divide by x minus 2. You are going to divide by x minus 2 to cancel that factor, and hence has a depressed equation of x squared, 7x squared minus x plus 1. Okay, so that is the next depressed equation. Okay, so basically every time you do this step where you use synthetic division, you are taking away a linear factor that contains the 0 that you are using. Okay, so what you need to take into consideration here is that you need to continue dividing. If you have a depressed equation that's still not a quadratic equation, that means that you need to do another synthetic division. You cannot use the same 0 again. You need to use another 0 to get a depressed equation. Okay, because if you use that 0 and you use it twice, it's on the second step here, we use -1 again, you are not going to get a remainder of 0, because now the depressed equation does not contain -1 as a 0. Okay. Right. So careful with this type of exercises. When you need to get a multiple depressed equation, make sure that if you are using a 0, that 0 belongs to the depressed equation. There are some some situations where you are going to repeat the 0. When you are going to repeat the 0? When the multiplicity of those zeros is greater than 1. Here we are allowed to use -1 just once because its multiplicity is 1. But if it would have happened that the multiplicity of either of these zeros is greater than 1, then we can use that same number as many times as the multiplicity. Okay, for a 0 with a multiplicity of 2, we can divide the polynomial and its depressed equation 2 times by that same 0, because the multiplicity tells us that that 0 is twice on the polynomial. All right, but since here we are just working with multiplicity of 1, or at least we are assuming at the beginning that we are working with a multiplicity of 1, you are going to use this 0 just once. And you guys have started with either. You guys have started with 2, and on the next division use -1. Okay, a lot of you use -1 as the first 0 and then +2. Okay, that's completely okay. But you can also use +2 and then -1, and you will get the same result. Right? So that's what I have for you as a review. Any question before we start unit number 7? All right. Okay, so unit number 7 is where we are going to talk about rational functions. All right. What is a rational function? A rational function has the following structure. So it is a function that it is made up by two polynomial functions in a fraction. So here we have a polynomial function as in the numerator, and we have also a polynomial function in the denominator. Okay, so that makes up a rational function. We have two polynomial functions in a fraction. From the library of function, we got the parent function. The parent function is 1 over x. Okay? 1 over x, this is the parent function of all rational functions. See that we have, in this case, we have a constant function here. Sometimes you can call this a polynomial function because of degree of 0. Okay? But I don't want to go discuss about what a polynomial function is here or not. Okay. What I want to point out is that in the denominator we have at least one polynomial function of degree of 1, a linear function, right? So this is what is important here. The denominator is a polynomial function, all right? We have a polynomial function in the denominator. All right. So what happened with a rational function? The first thing that happens is that we have one restriction, and that restriction is that the denominator x cannot be equal to 0. When x is equal to 0 in this function, the value is undefined. So there is a restriction. So the domain, it is from negative infinite. Here is the restriction from negative infinity to 0, union from 0 to positive infinity. See what's happening here. We are stopping at 0 as a right boundary from the first set of the domain. We are using a parenthesis because that means that 0 is not included, but 0 is a boundary. It's a stop there. Then we do a union, and we start again on with a left boundary of 0, but using a parenthesis, meaning that 0 is not included. Okay, and that goes until positive infinity. So that's the domain. So there is a restriction, and hence we have a domain. So basically, we are going to be working around this restriction and how its domain is modified, how the domain of the rational function is modified. From this, we go to this one just a moment. Let me take the graph. Okay, so here the graph of the parent function 1 over x. So what we want to take from this? First thing is we have how many key points would you need to draw this shape? Tell me on the chat, how many key points do you want to use to draw this shape? And here there is no 3. This time I will use one more, at least 4. Okay, as you can see here, we have like this shape with just 2 points. We can trace that curve. Okay, so we will need at least 4 key points, 2 for the left side and 2 for the right side. Okay, what is that thing that separates the left side from the right side? So rational function has something that it is called asymptotes. Asymptotes are not part of the function, are not part of the graph of the function, but they are properties, they are some properties that we can represent on the graph because asymptotes have a few key function or a few key importance in this graph. Okay, the first one is when we talk about the vertical asymptote. The vertical asymptote is the representation of the restriction of this polynomial. So the restriction is x cannot be equal to 0, right? So we can represent that in the graph as an asymptote. Okay, again, the asymptotes, when we just want to see this curve, or we want to see the graph of the function, we do not draw the asymptotes. But the asymptotes are there because the asymptotes are they are properties of the graph. So we tend to put them in the graph, knowing that they are asymptote and not part of the graph. Okay, so what is doing this vertical asymptote here? Well, this vertical asymptote is separating the left side from the right side. Also, is showing the restriction that the domain of this function has. Okay, the restriction of this domain is that x cannot be equal to 0. Hence, we can see it as an asymptote here. That's a vertical asymptote. Okay, we have two more types of asymptote. We have a horizontal asymptote or oblique asymptote. A graph, a rational function, we have either but not both horizontal or oblique asymptote. Okay, or we are not going to get there. So for our class, it will be either oblique or horizontal asymptote. Okay, this one has a horizontal asymptote, and the horizontal asymptote, it is located, okay, because here these are lines, we need equation to represent the asymptote. So the horizontal asymptote here is y equals 0, and the vertical asymptote equation is x equals 0. So those are the asymptotes. All right, so what the asymptotes do here? The asymptote here separates the left side from the right side, also the bottom side from the top side of the graph. But look what's happening with the graph. Look the behavior of the graph. On your graphing calculators, you can zoom, you can like go to the extreme left to see what happened with the graph, because we know that the graph will continue to the left because the domain says that we can continue to the negative infinity. But what is interesting is that our graph will continue, in this case to the left. It will continue to the left and towards the horizontal asymptote, but it never touch the asymptote. Okay, so the graph will always get closer and closer to the asymptote, but it never will touch it. Okay, so the effect of that is that this, the asymptote functions as a wall for that part of the curve of the function of the graph, but also it determines the behavior of the function of the graph, because with just 2 points, having 2 points here, we know that our graph need to pass through those 2 points, right? And because we have a horizontal function, a horizontal asymptote and vertical asymptote here, we know that the graph will tend to get closer and closer to the asymptotes, but it will never touch it. Then we can determine the shape of the graph. of each side. Okay, knowing that the graph or the curve in the left side need to pass through these 2 points. The curve never will touch or cross the asymptote, but it will get closer and closer to the asymptotes. Okay, so that's what the asymptotes are doing here, and that's how we will use the asymptotes to draw the graph. Okay, the asymptote will help us to determine the behavior of, or the shape or the behavior of the graph. Okay, so those are the asymptotes. Another property, another thing that we are going to see in the graph of the rational function are going to be, we could have holes on the graph. This one does not have any hole, but we are going to see example where we are going to find holes in the graph. Okay, so this is the general, this is the parent rational function. Okay, and now what we are going to do is to see, we are going to explore and study these properties on different rational functions. Okay, keep this in mind. Most important thing here is that we have a restriction, and the restriction is that the denominator can't never be equal to 0. Okay, from that restriction, we modify the domain of the function, and from that, from the modification of the domain, we can get the vertical asymptote. Right? So now we are going to study how to find holes in the graph, is there any, how to determine horizontal oblique asymptote, and how to find those equations. All right. From the worksheet of the day, you want to follow anytime you need to graph a polynomial function, you want to follow this step. Find the domain, find the holes, vertical asymptote, horizontal or oblique asymptote, intercepts, and then the behavior of near to the vertical asymptote and the end behavior of the graph. And with that, you can then determine or draw the graph of the function. Okay, and that's what we are going to do here. We are going to follow these steps: domain, holes, vertical asymptote, horizontal asymptote, oblique asymptote, intercept, so on, to do the graph. All right. So the step that are going to take to draw the graph of this polynomial function, of this rational function that we have here, I'm going to add one more step, one pre-step here. It will be try to simplify. Simplify. Yep, simplify. Simplify the function, then domain. From the domain, we are going to be able to determine vertical asymptote and holes. Then we are going to check for horizontal asymptotes or oblique asymptotes. Am I missing something? Okay. All right. Intercepts. Okay. Intercepts. With this information, the last step will be getting the key points. Remember that we need to have 4 key points. Key points are going to be taken from hole, is there any, and from the intercepts. If between holes and the intercept are not enough, then we will need to find more key points. So there are 4 key points. At least we are going to use 4 key points, 2 for the left side and 2 for the right side. Okay, and the right side and the left side are determined by the vertical asymptote. Okay, so so I should say that if we have one vertical asymptote, then the number of key points that we will need are going to be 4, 2 for the left side and 2 for the right side. If we have 3, then we will find 6 key points, 2 for the left side, 2 for the middle, and 2 for the right side, and so on. So I think that's it's going to be very likely that the amount of vertical asymptote that you are going to find on the exercises that you are going to be practicing on, and the amount of vertical asymptote is just 1, so 4 key points. But keep in mind, if you have more than 1 vertical asymptote, then you need to find 2 for each section of the graph. At least 2. Okay, it could be more, but at least 2 for each portion or section of the graph. Okay, so we are going to follow those steps to draw the graph of this rational function. So these are exactly the steps that you want to follow. Again, I'm going to try to explain each step. So I'm going to take more time. I'm going to write more than is you will have to write on your written work. Okay, but this is the guide or the step that you want to follow. Okay, then I'm going to do another exercises where I will try to write less, just to show you the amount of written work that you need to show for this exercise. Right. Now that I'm talking about that, I remember something. Okay, I need to stop for a moment and need to talk about going back to this exercise. Some of you might use different methods to find the factor form of each polynomial function, right? And that is completely okay, as long as you are able to show me how, or to show me or justify the use of different methods that are not taught in this class. Okay, so we are in a college algebra course, right? So we reached that level. What I'm teaching to a college algebra level, right? Yes, there are more techniques, more advanced techniques that will help us to do the factorization of any polynomial function. Okay, you might know those techniques and you can use them, right? But if you use them, you need to be able to justify and show me how you use those techniques. You need at least show me that you your work once you did your work without any external help. What I'm trying to say here is that in internet you can find a lot of help. There's PhotoMath, there is Symbolab. Those are apps on the cell phone, and then with your cell phone and the camera on your cell phone, you can take a picture or point to the exercises, and then in PhotoMath or Symbolab or any app that might help you to complete math exercises, it's going to show you the step to solve any exercise. Here, more specifically, it's going to show you how to factor a polynomial function. If you do that and you copy the step from those apps, you are going to be copying step for more advanced techniques. And I'm going to know if you are using advanced techniques. Okay, so if you use that, you could be losing points because if you are not able to show a complete understanding of the technique that you are using, then I will assume that you are using external help. Okay. The techniques and the strategy that I want you to be using are the ones that are taught in our class, because this is the level that we are teaching. It's going to be okay if you want to use other techniques, more advanced techniques, as long as you're able to show me your understanding of those techniques. As long as you are able to show me that you are not using any external help to do the exercises, right? So if you factor any polynomial by other methods that are not the method that are taught here, make sure to show your steps and justify each step, okay, based on your knowledge. If not, you are going to miss points, right? So yeah, that's what I wanted to say about that. That's something very important, because I know that the temptation is high to use external help to finish and to complete our math assignments. Okay, and that's not the purpose of this. The purpose is to prepare you for the future, not just to get good grades just because you found the answers on the internet, right? Okay, going back to our exercise. Let me just copy the equation here, or the function here. Okay, so first step, we are going to try to simplify. Okay, and I said we are going to try. This step not always going to be possible. But if it is possible, and if you do not simplify, then you are going to miss key information that is going to be important to determine vertical asymptotes and holes on the graph. Okay, so what we want to do here? So we want to do the factor for both part of the fraction. So from the polynomial that we have on the numerator, we can factor out a 3 and an x. So we have x plus 5. And in the bottom part of the fraction, the denominator, we can do fold factorization. Okay, so we have the factor form from both part of the fraction. And what's important here is that we have a common factor. That common factor is x plus 5. So what's gonna happen with x plus 5? So because we have a common factor, we can cancel them. Okay, so we cancel x plus 5, and now the simplified version of the function that we are working is 3x over x plus 2. All right, careful here. You need to remember, or you need to always take into consideration the original function that you are working on, or the equation of the original equation of the function. Why is that? Because now on the second step, we are going to determine the domain. And the domain, it is determined by the restriction. The restriction is that the denominator cannot be 0. Okay? And now you might be questioning which of these two we use. Do we use this denominator or this denominator? And the answer is that you need to take into consideration the original equation of the function. Okay, so we are going to take the denominator from the original equation, and we are going to say this can't be equal to 0. All right, and now we are going to treat this as an equation. Okay, when we have here a quadratic equation, and we are going to treat this as it will be equal to 0 to find those x values that makes this equation equal to 0. Based on those x values, we will identify the restriction. Okay, because we have the factor form already. That's what I'm going to do. That's what I'm going to use. Okay, so here you have two routes, right? Two pathways using the quadratic formula, or if you know the factorization of the quadratic equation, you can do this. All right. So again, we have a not equal sign here, but we are going to treat this as an equation, so we can identify those x values. So we have x plus 2 can't be equal to 0, hence we got x can't be equal to -2, and the same for the other factor. Can't be equal to 0, hence x can't be equal to -5. Alright, so here are the two restrictions, and how do we modify the domain? The domain will be from -infinity to -5. Careful here, we have -2 and -5. -5 is the lesser one between the two, or the smallest between the two, for -5. Then from -5 to -2, union from -2 to positive infinity. And that's the domain. All right? Any questions so far?
Can you show how to do it with the quadratic equation too?
Mm-hmm. Yep. All right. Again, we have a quadratic equation here, not equal to 0, but we are going to treat this not equal to 0 as an equal to 0, because we are looking for the x values. So our quadratic equation, the value of a is 1, the value of b is 7, and the value of c is 10. Okay, remember, if to be able to use the quadratic formula, we need to have the standard form of the quadratic equation, and on the other side we need to have a 0. So now we can use the quadratic formula. Okay. Okay. So we have here 40. No, this is 40 here, and this is 9. Okay. Plus minus 3 over 2. Then we have two possible values. Plus 3 over 2, and the other one it will be minus 3 over 2. So this gives us -4 over 2. This is equal to -2, and this gives us -10 over 2. So this is equal -5. And that's how you get those restrictions. So at the end, you are going to say x can't be equal to 2, x can't be equal to -5. I chose, yeah. And those are the restrictions. Okay. Here, using the quadratic formula. Here, using the factorization of the quadratic equation. The domain is the same. Okay, from -infinity to -5, union -5 to -2, union -2 to positive infinity. All right. So those are the two first steps, and now we are going to determine vertical asymptote and holes. Why am I looking for vertical asymptote and hole in the same step? It's because the vertical asymptote and the holes both are going to be determined by the restriction of the domain. So we have two restrictions. We have -2 and -5. Both of them could be vertical asymptotes or holes on the graph. How are we going to determine which of those two is a vertical asymptote and a hole in the graph? For that, we will need to use our simplified version. So in our simplified version, we have 3x over 2 plus x plus 2, right? So see what happened in the simplified version. -5 is not longer a restriction in the simplified version, because when we simplify the function, we eliminate or we cancel out the factor x plus 5 from the denominator. Hence, -5 here is no longer a restriction of the simplified version. Okay, and this is the tricky part, because you might think, well, then the domain is just, and the only restriction that we have here is -2. That's not true, because the original equation contains -5 as one restriction. This is just the simplified version. So what's gonna happen here? From the factor that we cancel, x plus 5, okay, let me put this in a better. Cancel the, is that how you wrote that? Cancel past part. Okay. Cancel factor is x plus 5. Okay, so that's the factor that we cancel, right? From there, from that factor, we got the restriction of x can't be equal to -5. All right. From the cancel factor is that we got the hole in or on the graph or in the graph. I don't know. Hole in the graph. Okay, right now I have a conflict with my English here. I don't know if on or in the graph, but you know more English than me, so you will know which one go there. So hole on the graph or hole in the graph. Okay, so from the cancel factor, we got a hole. That means that we have a hole in or on the graph. See what happened when we use -5 in the simplified version, because -5 is no longer a restriction on the simplified version. We can get a y value. Because we can get a y value, we will be able to find a coordinate, -5, comma, that y value. So hence we have a restriction. We have a location on the coordinate plane. So this is -3. So at the end, this is +5. So it means that the hole is located at -5, comma, +5. So there is the hole, right? So the hole is from one of the restrictions. If those one of those restrictions or those restrictions from the original equation are no longer restriction on the simplified version, that means that we have a hole in or on the graph, right? So that's the hole. What is the meaning of the other restriction that are still restriction on the simplified version? Well, those restrictions are vertical asymptotes. So the vertical asymptote, and you need to remember that vertical asymptote is a line. So we need an equation. The restriction is x can't be equal to -2. Hence, the vertical asymptote equation is x equal 2. From the restriction x can't be equal to, we got the equation of the vertical asymptote, which is x equals 2. Okay, because that is the location of the vertical asymptote. Any question in this step? All right. So horizontal asymptote or oblique asymptote. So we will have either one, but not both. You see, 3, 8. Rachel, are you asking about step number 3? Rachel, can you hear me? Okay, so the vertical asymptote, once we identify a hole in or on the graph, so we have two restrictions. We have -2 and -5. One of these is a hole on the graph because when we look at the simplified version, -5 is no longer a restriction on the simplified version. That means that -5 is a hole on the graph. The remainder restrictions, in this case, it's just x equal or x cannot be -2. That restriction that is still a restriction on the simplified version because we cannot use -2 here. Otherwise, we will have an undefined value. That restriction that stay a restriction in the simplified version, it is the vertical asymptote. But here on the vertical asymptote, we want to give an equation for the vertical asymptote. So see that now I'm using equal to 2 and not equal to 2. Okay? Because vertical asymptote here, I'm referring that at x equal 2, we have a vertical asymptote. So that is the equation of the vertical asymptote. Okay? The part that is confusing is that the only thing that we need to change is just the sign, equal to not equal to equal. Okay? But the concept, what the meaning of this is that the not equal is a value that we cannot use on the function. And when we use x equal to 2, it means a vertical asymptote, a vertical line at x equal 2 that prevents the graph to pass through there. Does that answer your question? All right. Okay. So how are we going to determine horizontal asymptote or oblique asymptote? So we have three cases. And those cases are based on the degree of the part of the rational function. Okay, so you are going to compare degree of numerator with degree of denominator. Numerator, denominator. All right. So this is what we are going to do. We are going to compare the degrees of the numerator and the denominator. Case 1. And this case is going to give us a horizontal asymptote with equation y equal to 0. That case is when, so I'm going to use degree of the numerator as dn. Degree of the numerator is going to be dn, and degree of denominator is going to be dd. All right, when dn, degree of the numerator, is less than degree of denominator. When that happens, we have a horizontal asymptote, and that horizontal asymptote is going to be, or the equation of the horizontal asymptote will be at y equals 0. Going back to the parent function, the degree of the numerator here is 0. The degree of the denominator is 1. 0 is less than 1. Hence, the horizontal asymptote is y equals 0. Okay? Case 2. Horizontal asymptote, we will have horizontal asymptote with an equation of the horizontal asymptote by leading coefficient of numerator over leading coefficient of denominator. Okay? When that happens, when degree of numerator is equal to the degree of the denominator. Okay? Leading coefficient of numerator over leading coefficient of the denominator. Case number 3. We are going to have an oblique asymptote with a linear equation of that oblique asymptote. Okay? So we will have a linear equation that represents the oblique asymptote. When that's going to happen? When the degree of the numerator equals, or I should say, let me put it here this way. So when the degree of the numerator is 1 degree greater than the degree of the denominator. In other words, if we add 1 to the degree of the denominator, then that value is equal to the degree of the numerator, then we will have an oblique asymptote. And the oblique asymptote equation, it will be a linear equation. Okay? If we don't have anything that is not on these three cases, that means that we don't have horizontal or oblique asymptote. Okay, if we have that the degree of the numerator is 10 times greater than the degree of the denominator, then there is no horizontal or oblique asymptote. Okay, so those are the three cases. In this exercise, we are going to see which of the three cases we have. Any question? Okay, so I want you to tell me what type of equation or what is the case for this exercise. Case 1, 2, or 3. Okay, what is the case? Which of the three cases is this exercise?
Are we supposed to use the original one or the simplified one?
The original one.
Okay.
Okay, not so sure if you can see this well, so let me zoom on this. Okay. So remember, you want to compare the degree of both numerator and denominator. The degree of both is 2. So that means that the degree is equal. So we are in case number 2. That's correct, Rachel. Yes, case number 2. So that means that we have a horizontal asymptote. So we have a horizontal asymptote and the equation is going to be 3 over 1. The leading coefficient of the bottom of the denominator is 1. So y equals 3. So that is the equation of the horizontal asymptote. Okay, so that's the number 4. Let's find the intercepts. Any questions so far? All right, so we know that we have x-intercepts and we have y-intercepts. Let's start with the x-intercepts. At this point, you want to use the simplified version. Let me just copy it, put it here. Oops. So what is the main property of the x-intercept? Is that the y value is 0. So if all this is equal to 0, then we need just to solve the numerator for 0. Okay, so here are some shortcuts that you can take. When you are looking for the x-intercepts, see that at the bottom how we solve here for x. Because here we have an equal sign, we can multiply both sides by the denominator. So we can multiply both sides by x plus 2. But what happened on the left side? There is 0. So at the end, the denominator here, it won't make any difference on finding the x-intercepts. So you can do a shortcut, and instead of writing the entire simplified version, just just take the numerator, because here this is going to be get cancelled. Take the numerator equal to 0, and then find the value of x that makes the entire numerator equal to 0. From here, we can take another important property. If there is no variable in the numerator, then there is no x-intercept. Okay, I'm not going to write this here because I don't want to confuse you, but we have some examples where you are going to see there's no x-intercepts. If in the numerator you are not seeing any x variable, means that there is no x-intercepts. Here, the intercept is the x-intercept is x equals 0. Hence, the location of the x-intercept is 0, 0. This is the origin, so meaning that the x-intercept and the y-intercept both are the same. So I'm going to stop here. I'm not going to find for the y-intercept because you are going to see that the y-intercept is also in the origin. So we have only one intercept. Both x and y-intercept are in the same point, are in the origin. Right. So now we need the key points to draw the graph. So here we have just one vertical asymptote. So we need 4 key points. And this is how we are going to do it. We know that we need we have a left side and we have a right side. How we separate left side and right side? We use the vertical asymptote. The vertical asymptote here is at x equal -2. So that's the vertical asymptote. So we need to find 2 points on the left side of the vertical asymptote and 2 points on the right side of the vertical asymptote. Okay, what we have so far? We have 2 locations on the graph. We have the hole. The hole is at -5, is -5, +5. So that means that the hole is on the left side. How I know that the hole is on the left side? Because the x value is less than -2. Sorry, this should be -2. Is it -2? Let me double check that I'm correct. Vertical asymptote. Oops, I make a mistake here because the vertical asymptote is -2. Sorry about this. Okay, but vertical asymptote, I made a mistake. I said that the vertical asymptote, it was x at +2. That's incorrect. The vertical asymptote is at x equals -2. Okay, because -2 is the restriction for the function. Okay, so again, vertical asymptote is at -2. That's what we have here. Okay, -2. Okay, -5, which is the x value of the hole, is less than -2. So that means that that location is on the left side. We are going to take the hole as one of those key points. Remember, the hole is something that is not part of the function, so we are going to use an open circle there. We have an x and y intercept. We have just one intercept, and that intercept is on the origin. Zero and 0. So that intercept is on the origin, and the intercept is a point on the graph. So we are going to use a solid dot there. Okay. So let me put those points here to know what we have so far. So 0 and 0, and then for the whole is -5, +5. So open circle here. All right. So that means that we need to find one more point on the left side and one more point on the right side. So on the left side, I'm going to select x equals -3. Why x negative 3? Because it's the next to -2 when we go to the left. Okay. So with x -3, and I'm going to use here the simplified version because I just want to get the location of this point. So using the simplified version is going to be enough. Okay. So remember, we used the whole first, and then now we are using x equal -3. So we got -3 here over 1, and this is 9 equals, this is equal 9. So that point is -3,9. Okay. So that point, it is here. It is a point. And then we have the x-intercept, and now for the other point on the right side, I'm going to select x equal 1, okay, because we already got, we already used x equals 0 because that's the intercept. So now I'm going to evaluate the function with x equal 1. So it will be 3 over 3 times 1, then 1 plus 2. All this is going to be 3 over 3. This is equal to 1. So the point that we got here is 1 over 1, 1. We go here and we put that number here. So I will need to move this. So it is here, 1, 1. All right. So we have the 4 key points. We have already the vertical asymptote in the graph. Now what we need is to put the other asymptote, which is the horizontal asymptote. The horizontal asymptote is at y equal 3. So I'm just going to take this. There is the horizontal asymptote. Okay. Let me take this and move this because it's looking like a mess here. So okay, I think that's cleaner. So what we have so far is the horizontal asymptote, the vertical asymptote, and the 4 points, or at least the 4 locations, because one of those key points is a hole. So the last thing that we need to do is remember the graph need to pass through these points, and the asymptote determine the behavior of the graph or the ends point. So it will be something like this, And this is not perfect, this is just a representation. And it will be something like this. Nope, that is very bad. Okay, and that would be the sketch of this graph. Again, it's a representation, it is not perfect, but we want to see at least that you're able to sketch the shape of the graph. Okay, identifying the hole, identifying the asymptotes, okay, and the end behavior, remember, that are going to be determined by the asymptotes. The asymptote, remember what is the effect of the asymptote. The graph always wanted to touch the asymptote. It will always approach to the asymptote, but it will never reach them out. Okay, it will never touch the asymptote. Yeah, and that's for exercise. Let me see if I can show you again all the steps. Okay. All right. So as a review, we have 6 steps to follow in order that will help us to sketch the graph. Simplify, identify the domain, vertical asymptote and hole, horizontal or oblique asymptote, intercept, and key points. Okay. First, we start with the simplification. Okay. To do the simplification, do the factor form of both numerator and denominator and see if there is any common factor. Those common factors are going to get cancelled. Then, to determine the denominator, we take the denominator from the original equation, and we set the denominator not equal to 0, and then we treat that not equal as an equation, because we are going to find those x values that makes the denominator equal to 0. From there, we get the restrictions. Okay, now that we have the restriction, we can determine the domain, but then we need to we need to determine if those restrictions are vertical asymptote or holes. A hole, we know that a hole is going to be, we are going to get a hole for any cancel factor. Okay, the cancel factor of the denominator here was x plus 5. The restriction, or the 0 of that linear factor, is x is -5. Okay, so that restriction of x can't be equal to -5 now becomes a hole in the graph, because we can evaluate -5 in the simplified version. In the simplified version, we can plug in -5 into x and we get a y value. Hence, we have the location of a hole. It is a hole because -5 is not part of the domain, but in the simplified version, we are getting a value for the y value, or we're getting a y value or a value for the function in the simplified version. Okay, so that's 5. The vertical asymptotes are going to be all the other restrictions that are not holes. Okay, and we take those restrictions, and to create the equation is going to be x equal to the value of the restriction. Do not forget this negative sign as I did on this exercise. Next step, we need to determine if we have horizontal, oblique asymptote, or neither one. We have 3 cases. We are going to compare the degree of the numerator and denominator. When the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote at y equals 0. When they are the same, degree of the numerator equals degree of the denominator, we have a horizontal asymptote at the equation will be the leading coefficient of the numerator divided by the leading coefficient of the denominator. The case number 3 is the only one where we are going to have an oblique asymptote when the degree of the numerator is 1 degree greater than the degree of the denominator. When that happens, the equation of the oblique asymptote is going to be a linear equation. We are going to see how we are going to get that value, that equation there. in our case, in this exercise, both degree are 2, numerator and denominator, hence the location of the horizontal asymptote is at y equal 3 over 1, which is 3. To do the intercept, we do the same as we have been doing from the beginning. X-intercept, the y value is 0, y-intercept, the x value is 0. In this case, we got an intercept on the origin, so both x and y intercept are the same. Then for the key points, we take into consideration the vertical asymptote. In this exercise, we just have one vertical asymptote, so we are going to find at least 2 points on the left side of that vertical asymptote and 2 points on the right side of that vertical asymptote. Left and right side are determined by the x values. Any x value less than the vertical asymptote is going to give us a left side point, and any x value greater than the vertical asymptote value is going to give us a right side point. Okay. Key points we are going to consider as a key point holes and intercepts. If we have a hole, we can use its location as a point for the graph, but remember that we need to use an open circle there. Okay. Any other remainder 0 that we need to, any other key point that we need to find, we are going to select specific x values to get those points. In this occasion, I use -3 and x equal 1, with the first one for the left side and the second one for the right side. Once we got those key points, 2 for each curve, and we have the asymptotes in the coordinate plane, now we are more comfortable or more confident on the shape of the graph. The shape of the graph is the graph need to pass through those points, or at least to those locations, and the end behavior of the graph, or the overall shape of the graph, will be determined by the asymptotes. The graph always wants to touch the asymptote, so it will go towards the asymptote, but we never reach out the asymptotes. And that is how we got the graph. Any question? Okay, so this is a good time to take a break. When I get back from the break, I will do an exercise where we are going to get an oblique asymptote, and I'm going to show you how you are going to find the equation of the oblique asymptote. And then we will do a few more type of exercises that you are going to see on the Alex homework, so I can help you understanding those type of exercises. And after that, I have Rachel, you have a question, I have your question here, if you can stay. We will go over your question, and if anyone wants to also see the answer of that question, you are welcome to stay. And yeah, that will be all for today, but right now we are going to take our break, 5 to 10 minutes, and then we are going back. We are going to see another exercise, another example. If you have any question, post those questions on the chat or just speak up. I'm going to answer your question, okay? I will get back here in 5 to 10 minutes.